Imagine a space rock the size of the Eiffel Tower, hurtling through the abyss of space at 101,000 kilometers per hour, its trajectory intersecting with the orbit of our planet. This is not the plot of a Hollywood blockbuster. This is the reality that humanity has come face to face, and the name of this reality is Bennu. In September 1999, as the world was preparing for the new millennium and people were massively stocking up on canned food in anticipation of the Y2K computer apocalypse, a team of astronomers on the Linear project accidentally discovered something far more disturbing. A small dot of light appeared in the telescope images, moving among the fixed stars. At first, it was given the boring designation 1999 RQ-36. But later this asteroid was given a name that is now known to millions of people around the world, Bennu, in honor of the ancient Egyptian bird associated with the sun, creation, and rebirth. The irony of this name becomes obvious when you understand that this cosmic object can bring not revival, but destruction. Bennu is not just some rock in space. It is a carbonaceous B-class asteroid, one of the darkest objects in the solar system, reflecting only 4% of the sunlight that hits it. Its diameter is about 490 meters, about the height of 5 football fields lined up in a row, or the height of the Empire State Building. This colossus weighs about 78 billion kilograms. For you to understand the scale, it is like 78,000 aircraft carriers of the Nimitz class, or the entire fleet of all countries of the world, multiplied several times. What makes Bennu particularly cunning is his orbit. The asteroid completes an orbit around the Sun in 436.604 Earth days, just over a year. Its trajectory is so close to Earth's orbit that it regularly crosses our cosmic path. Every 6 years, Bennu approaches our planet at a relatively close distance in cosmic terms. That's why scientists have classified it as a potentially hazardous asteroid, one of about 2,000 known space objects that could someday threaten Earth. But here's what really keeps NASA scientists up at night: the Yarkovsky effect. This phenomenon is named after the Russian engineer Ivan Osipovich Yarkovsky, who as early as the 19th century suggested that asteroids could change their orbits when exposed to sunlight. Imagine this. One side of Bennu is heated by the sun during the day, and then when it turns and is in shadow, it begins to cool down and radiate heat into space. This radiation creates tiny jet thrust, like a microscopic cosmic engine. Sounds insignificant? Over millions of years, this tiny force can significantly change the trajectory of an asteroid. Every year, Bennu moves about 284 meters away from where it should be if gravity alone were taken into account. 284 meters isn't that much on a cosmic scale, right? But when it comes to whether an asteroid nearly half a kilometer in size would hit a planet with a diameter of 12,742 kilometers millions of kilometers away, those 284 meters could mean the difference between a flyby and a catastrophic collision. It's like trying to hit a particular apple on a tree with a needle while standing a few kilometers away. The slightest deviation completely changes the result. It is the Yarkovsky effect that makes long-term prediction of Bennu's trajectory so difficult. Scientists have been observing this asteroid for decades, building mathematical models, taking into account the gravitational influence of all the planets of the solar system, the solar wind, light pressure, and dozens of other factors. And after all these calculations, they came to an alarming conclusion. There is a 1 in 2,700 chance that Bennu will collide with Earth sometime between today and the year 2300. 1 in 2,700. How to estimate this probability? Let's think about it. This is about 0.037%. Sounds tiny, almost insignificant, right? For comparison, the probability of being killed by lightning in a lifetime is about 1 in 15,000. This is 6 times less than the probability of encountering Bennu. The odds of winning the lottery jackpot are about 1 in several million, making facing Bennu an event 1,000 times more likely than winning the grand prize. If you got on a plane with a 1 in 700 chance of crashing, you'd never fly. For comparison, the chance of dying in a plane crash is about 1 in 11 million. But when it comes to an asteroid that can destroy an entire continent or cause a global catastrophe, even such a small probability makes you think seriously. It's not about whether it will happen to you personally, it's about the fate of the entire civilization. And here's what is especially important to understand. Scientists have identified several specific dates when the risk of a collision reaches its maximum. The most dangerous of them is September 24th, 2182. On this day, the probability of a strike is approximately 1 in 2,750. What would happen if Bennu did collide with Earth? Let's be honest, it will be a disaster of unprecedented proportions, but not the end of the world in the literal sense. Bennu is not big enough to cause the extinction of all mankind, like that 10-kilometer diameter asteroid that wiped out the dinosaurs 66 million years ago. But the consequences will be catastrophic at the regional and possibly global level. Imagine the moment of impact. Bennu enters the Earth's atmosphere at a speed of about 12 kilometers per second, which is 35 times faster than the speed of sound. Friction with the atmosphere heats the asteroid's surface to temperatures of tens of thousands of degrees, but the object is too massive to burn up or slow down significantly. In a matter of seconds, it passes through the entire atmosphere and crashes into the Earth's surface. The impact energy will be equivalent to an explosion of 1,200 to 1,500 megatons of TNT. By comparison, the most powerful nuclear bomb ever detonated by man, the 1961 Soviet Tsar Bomba, had a yield of 50 megatons. That is, Bennu's punch will be 24 to 30 times more powerful. If an asteroid hits the ocean, which is more likely given that water covers 71% of the Earth's surface, it will create a tsunami of monstrous proportions. Waves tens and possibly hundreds of meters high will rush in all directions at the speed of a jet plane. Coastal cities thousands of kilometers away from the point of impact will be washed off the face of the Earth. New York, Tokyo, Shanghai, Mumbai, Sydney. Any major coastal metropolis can be destroyed in minutes. Millions, perhaps tens of millions, of lives will be lost in the first hours after the impact. If Bennu falls to land, the consequences will be somewhat different, but no less catastrophic. At the point of impact, a crater is formed with a diameter of about 7 kilometers and a depth of more than a kilometer. Everything within a radius of several tens of kilometers from the epicenter will instantly evaporate. Rocks, soil, buildings, forests, people. Everything will turn into superheated plasma. The shock wave will destroy buildings and kill all life within a radius of 1 or 200 kilometers. The heat radiation from the impact will cause massive fires hundreds of kilometers away, turning entire regions into a fiery inferno. But this is just the beginning. The impact will release billions of tons of dust, ash, and vaporized rock into the atmosphere. This material will rise into the stratosphere and spread throughout the planet, creating an effect similar to nuclear winter. Sunlight will be partially blocked for months, possibly years. The temperature on the Earth's surface will drop by several degrees. Photosynthesis will slow down, crops will die, and global hunger will begin. Ecosystems around the world will be destroyed. The economy will collapse. There will be mass migrations, wars for resources, chaos. It sounds like an apocalyptic movie script, but it's a realistic scientific forecast based on computer modeling and the study of traces of past space disasters. The history of the Earth is full of examples of such events. The famous Tunguska meteorite of 1908, which exploded over Siberia, had an energy of only 5 to 30 megatons, tens of times less than the potential Bennu impact. But it felled trees over an area of more than 2,000 square kilometers. And the meteorite that exploded over Chelyabinsk in 2013 had a diameter of only about 17 meters and an energy of about 400 to 500 kilotons. But the shock wave from its explosion damaged thousands of buildings and injured more than 1,500 people. Now multiply the scale of the Chelyabinsk meteorite by a factor of thousands, and you get a rough idea of what Bennu can do. It's not the end of the world, but it could be the end of our civilization as we know it. The survivors will be thrown into a world more like the pre-industrial era, where they will have to rebuild society among the ruins of the old one. But here's what is surprising. Despite all this threat, humanity does not sit idly by. What's more, we did something unprecedented in history. We sent a spacecraft all the way to Bennu to study it up close, understand its nature, and even take samples of its surface. This mission is called OSIRIS-REx, and it has become one of the most ambitious and successful space projects of the 21st century. OSIRIS-REx is an acronym for Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer. The name sounds complicated, but the essence is simple. It was the first American spacecraft created specifically to visit an asteroid and bring samples of its material back to Earth. The mission, worth more than $1 billion, was launched on September 8, 2016 from the Cosmodrome at Cape Canaveral in Florida. The Atlas V rocket carried a spacecraft the size of a large car and weighing 2,100 kilograms onto the trajectory of rendezvous with Bennu. The journey took 2 years. OSIRIS-REx could not fly in a straight line. It does not work like that in space. It first performed a gravitational maneuver near Earth in September 2017, using our planet's gravity as a giant slingshot to gain speed and change its trajectory. And so, on December 3rd, 2018, after a journey of 2 billion kilometers, OSIRIS-REx reached Bennu and entered orbit around the asteroid. It was a historic moment, the first time a spacecraft had entered orbit around such a small celestial body. Bennu's gravity is so weak, about 500,000 times weaker than Earth's, that the spacecraft orbited at just a few centimeters per second, slower than a human. OSIRIS-REx spent the next 2.5 years carefully studying Bennu from all angles. The spacecraft's cameras took millions of pictures, creating a detailed map of the asteroid surface. Every rock, every crack, every crater was recorded with unprecedented accuracy. Scientific instruments measured the composition of the surface, temperature, and structure of the material. And what the scientists found was both fascinating and disturbing. Bennu turned out to be not a solid block of stone, as many had assumed, but a so-called rubble pile. A loose accumulation of rocks, boulders, and dust, loosely held together by gravity and perhaps small cohesive forces. This means that the asteroid was once part of a larger body that collapsed in a collision, and then its debris came back together. The surface of Bennu is dotted with boulders the size of a house. Some reach 50 meters across. For the mission team, this posed a huge challenge: where to find a safe place to land and collect samples. But OSIRIS-REx also discovered something surprising. Bennu turned out to be an active asteroid. Jets of particles periodically burst out of its surface, small pebbles and dust, which are thrown into space. Scientists have recorded hundreds of such emissions. The reasons for this phenomenon are not completely clear. Perhaps it is due to thermal stresses when the rock is heated by the sun and then cools quickly, or to the destruction of minerals under the influence of cosmic radiation. These ejections added to the danger of the mission. Imagine that you're trying to gently touch the surface and rocks suddenly fly out of it. And yet, after careful study, the team chose a place to take samples. It was called Nightingale, a small, relatively flat area in the crater in the northern hemisphere of Bennu. On October 20th, 2020, OSIRIS-REx made a historic landing on the surface of an asteroid. Well, not exactly a landing, rather a gentle touch. The spacecraft extended a 3.35-meter long robotic arm with a round head 30 centimeters in diameter at the end. This head was equipped with a sampling mechanism. When it came into contact with the surface, it released a jet of compressed nitrogen, which disturbed the surface material, and this material was collected in a special container. The whole process took only about 6 seconds, but those 6 seconds are the culmination of 4 years of work. And what is most surprising is that the OSIRIS-REx arm sank almost half a meter into Bennu's surface. The material turned out to be so loose that if a person tried to stand on Bennu, he would fall like a snowdrift. This has completely turned scientists' ideas about the structure of such asteroids upside down and has important implications for any future attempts to deflect a dangerous asteroid. You can't just crash it with a rocket or blow it up. You need to understand its internal structure. OSIRIS-REx collected approximately 250 grams of material from Bennu's surface, more than planned. This may seem like a small number, but for scientists, it is a treasure. Each grain of this material is a time capsule that stores information about the formation of the solar system 4.5 billion years ago. After successfully collecting samples, the spacecraft sealed the container and began preparing for the return journey. On May 10th, 2021, OSIRIS-REx said goodbye to Bennu and set off on the long journey home. The return journey took another 2.5 years. And so, on September 24th, 2023, exactly 7 years after launch, the sample capsule entered the Earth's atmosphere over Utah at a speed of 44,000 kilometers per hour. The parachute opened perfectly, and the capsule landed gently in the desert, where it was immediately picked up by the recovery team. The samples were taken to a purpose-built laboratory at NASA's Johnson Space Center in Houston, where scientists began scrutinizing them. What did they find in these samples? The material from Bennu turned out to be rich in organic compounds, molecules containing carbon, hydrogen, oxygen, and other elements that are the building blocks of life. Amino acids were found, the very molecules that make up the proteins of all living organisms on Earth. Simple sugars, nitrogenous bases, and other organic compounds have been discovered. This does not mean that there is life on Bennu, but it does support the theory that asteroids may have delivered the chemical components necessary for life to arise on early Earth. Water was also found in the samples. More precisely, water-containing minerals, where water molecules are included in the crystal structure. This is important because it shows that asteroids like Bennu may have been the source of water on early Earth when our planet was forming and was too hot to hold water on the surface. It turns out that the oceans of the Earth, from which life once arose, could have been delivered by such cosmic messengers. But beyond the scientific significance, the OSIRIS-REx mission also had a practical purpose: to help us better understand Bennu in order to more accurately predict its future trajectory and, if necessary, develop ways to defend against it. The data collected by the device allowed scientists to refine Bennu's orbit with unprecedented accuracy. They measured the Yarkovsky effect directly, confirming theoretical predictions and improving models. We now know more about Bennu's trajectory than any other asteroid in the solar system. And this knowledge is critically important because for the first time in its history, humanity is developing real technologies for planetary defense. We are no longer helpless in the face of a cosmic threat. In November 2021, NASA launched the DART mission, Double Asteroid Redirection Test, which can be translated as Double Asteroid Redirection Test. The goal of this mission was simple and daring at the same time: to crash a spacecraft into an asteroid and change its orbit. The target of DART was a small asteroid with a diameter of 160 meters named Dimorphos, which is a satellite of the larger asteroid Didymos. On September 26, 2022, the DART spacecraft, weighing about half a ton, crashed into Dimorphos at a speed of about 22,000 kilometers per hour. This was the first time that humanity had intentionally changed the trajectory of a space object. And it worked. The impact changed the orbital period of Dimorphos around Didymos by as much as 33 minutes, much longer than expected. The mission proved that a kinetic impactor, a spacecraft used as a projectile, can be an effective tool for planetary defense. But will it work with Bennu? This is a difficult question. Dimorphos is a relatively small and dense asteroid. Bennu is much larger, almost 3 times wider and tens of times more massive. In addition, its loose rubble pile structure means that the impact may not transmit momentum efficiently. The energy may simply dissipate, crushing some of the material, but not changing the trajectory of the entire asteroid much. It's like the difference between hitting a billiard ball and hitting a sandbag. In the first case, the whole ball will roll. In the second case, the energy will be absorbed and dissipated. That is why scientists are considering various scenarios for protecting against Bennu, should it ever become necessary. One approach is the so-called gravity tractor. The idea is simple: place a sufficiently massive spacecraft near the asteroid for a long time. The gravitational attraction between the spacecraft and the asteroid, although tiny, can slightly change the asteroid trajectory over years or decades. The advantage of this method is that it does not require contact with the surface and does not depend on the internal structure of the asteroid. The disadvantage is that it takes a lot of time. So this method is useless if there are only a few years left before the collision. Another approach is the use of solar energy. It would be possible to place a large mirror or lens on or near the surface of the asteroid that would focus sunlight on a specific point on the surface. The heated rock will begin to evaporate and be ejected into space, creating jet thrust similar to a tiny engine. Over time, it could also change the asteroid's orbit. This method is particularly well suited to carbonaceous asteroids like Bennu, which contain volatiles. There's also a more radical approach: nuclear deviation. No, it's not about blowing up an asteroid, as in the Hollywood movie Armageddon. Blowing up an asteroid is a terrible idea, because instead of one big threat, you'll end up with many smaller fragments, many of which could still crash into Earth. Instead, a nuclear charge can be detonated near an asteroid without touching it. The thermal radiation from the explosion will vaporize part of the asteroid's surface, and this ejection of material will create an impulse that will push the asteroid in the other direction. The advantage of this method is that it can give a very large boost in a short time, making it a suitable option for emergency situations where preparation time is short. But all of these methods require one critical factor: time. The sooner we detect the threat and take action, the less effort it will take to deflect the asteroid. A change in trajectory of a few millimeters per second decades before a potential collision could cause an asteroid to miss Earth by millions of kilometers. But if time is short, much more powerful and risky methods will be required. In Bennu's case, we have time, a lot of time. The most dangerous date is 2182, which is still more than a century and a half away. Our great-grandchildren or great-great-grandchildren will have technology at their disposal that we can only dream of today. Perhaps by then, humanity will have permanent bases on the Moon and Mars, a fleet of powerful spacecraft, and decades of experience in controlling asteroid trajectories. Perhaps asteroid mining missions, and Bennu is rich in carbon, water, and various metals, will give us practical skills in working with such objects. On the other hand, 157 years is not so much on the scale of human civilization. In 1868, 157 years ago, there are no cars, no airplanes, no electricity in homes, let alone computers or space travel. Who knows what civilization will be like in 2182? Will it be more developed? Or will we face regression due to climate change, resource depletion, or other global crises? The question remains open. What is particularly interesting about Bennu's situation is the philosophical and ethical aspect of the problem. We know about the potential threat in advance, generations before it can materialize. But the probability of a collision is still relatively low. Is it worth investing billions of dollars in planetary protection right now, when that money could be used to solve more pressing problems: climate change, poverty, disease? On the other hand, if we do not prepare and the clash does occur, the consequences will be catastrophic and future generations will curse us for inaction. This is a classic risk management problem. How do you balance the low probability of a highly catastrophic event with its potential consequences? The insurance industry has long solved this dilemma. We pay premiums knowing that we will probably never use insurance, but having it in case of the worst. Planetary protection is the insurance of all mankind. The only question is what kind of premium we are willing to pay for it. Fortunately, investing in planetary protection has collateral benefits. Missions like OSIRIS-REx not only help us understand the threat from asteroids, but also expand our scientific knowledge of the origin of the solar system and life. They stimulate the development of technologies that are used in other areas. They inspire a new generation of scientists and engineers. In addition, international cooperation in planetary defense unites countries around a common goal, which in itself is valuable in our divided world. And it must be said that humanity takes this threat seriously. International organizations and working groups were created to coordinate planetary defense efforts. NASA has established the Planetary Defense Coordination Office, which tracks potentially hazardous asteroids and plans missions to study them and, if necessary, deflect them. The European Space Agency, Japan's JAXA, China's CNSA, and other space agencies are also actively involved in these efforts. There is an international asteroid warning network that coordinates observations of dangerous objects from around the world. The catalog of known near-Earth asteroids is constantly growing thanks to increasingly powerful telescopes. In 1990, we knew that there were only a few hundred such objects. Today, more than 30,000 of them are known, and new ones are discovered every week. The goal is to find and catalog all asteroids larger than 140 meters, large enough to cause a regional catastrophe in a collision. It is believed that we have already found about 90% of asteroids larger than a kilometer in size, the most dangerous, capable of causing a global catastrophe. But among medium-sized asteroids like Bennu, we only know about half of the estimated total. This means that somewhere out there, in the darkness of space, there are thousands more asteroids that we know nothing about, and some of them may be on their way to colliding with Earth. Perhaps right now, at this very moment, some kind of asteroid is hurtling towards us, and we only know about it years, months, or even weeks before the impact. This is not a reason to panic, but a reminder of why continued monitoring of the sky is so important. In this context, Bennu can almost be called a gift. We know about it, we know its orbit, we have studied it up close, and we have more than a century to prepare if we need to act. This allows us to use Bennu as a test case, a laboratory to practice our planetary defense strategies. Everything we learn about Bennu applies to thousands of other similar asteroids, including some we don't know about yet. But let's go back to Ben himself and his story. Where did this asteroid come from? How did he end up in an orbit that crosses the path of the Earth? Scientists believe that Bennu formed in the main asteroid belt between the orbits of Mars and Jupiter about 1 to 2 billion years ago. Initially, it was part of a much larger asteroid, perhaps tens or even 100 kilometers in diameter. This parent asteroid has existed since the formation of the solar system 4.5 billion years ago, preserving in its material the primordial material of the solar nebula, the cloud of gas and dust from which the sun and all the planets formed. But about 1 billion years ago, a catastrophe occurred. Another asteroid, flying at great speed, crashed into Bennu's parent body. The energy of the collision was so great that it shattered the large asteroid into thousands of fragments. Some of these fragments flew in different directions. Some fell into the sun or were ejected from the solar system. But many came together again under the influence of mutual gravitational attraction, forming new smaller asteroids. One of them was Bennu. But how did Bennu get from the asteroid belt to an orbit close to Earth? This is a long story that stretches for hundreds of millions of years. The main asteroid belt is not a perfectly stable place. There are so-called resonances with Jupiter, regions of orbits where the gravitational influence of the giant planet creates periodic perturbations. An asteroid that happens to be in such a resonant zone gradually changes its orbit more and more until it is ejected from the asteroid belt. That's probably what happened to Bennu. The resonance with Jupiter slowly changed its orbit until it became elongated enough to cross the orbit of Mars. Gravitational encounters with Mars then continued to change their trajectory. Millions of years later, Bennu found himself in an orbit that crosses the Earth's orbit, where it is now. This journey took hundreds of millions of years, but in the end, Bennu ended up in a part of the solar system where it could become a threat to our planet. And here's another surprising fact. Bennu's surface is extremely ancient, but also very young. Sounds paradoxical? Let me explain. The material that makes up Bennu is really very old. It is 4.5 billion years old. But the asteroid itself in its current form formed only about 1 billion years ago after the destruction of its parent body. And the surface layer we see today is even younger. Space weathering, bombardment by micrometeorites, exposure to the solar wind and cosmic rays, constantly renews the surface. The rocks turn over, the dust moves, and fresh material from the bowels comes to the surface. What's more, data from OSIRIS-REx showed that Bennu's surface is changing much faster than scientists thought. Boulder-sized rocks move from one place to another in just a few years. The asteroid's rotation, thermal stresses, tiny micrometeorite impacts, and the particle ejections mentioned earlier all make Bennu's surface a surprisingly dynamic environment. If you could observe Bennu for decades, you'd notice how its surface slowly reshapes, similar to how sand dunes on Earth change shape when the wind blows. Another discovery made by OSIRIS-REx concerns the temperature on Bennu. During the day, when the sun illuminates the surface, temperatures can reach 127 degrees Celsius, almost like boiling water. At night, the temperature drops to minus 73 degrees Celsius. This temperature fluctuation of 200 degrees occurs every 4.3 hours. This is how long a day lasts on Bennu. So fast it rotates. Such extreme temperature changes create enormous mechanical stresses in the rock, leading to its cracking and destruction. This is one of the mechanisms that constantly change the surface of the asteroid. Now imagine what it would be like to be on Bennu. Gravity 500,000 times weaker than Earth's means you'd weigh less than a gram. A slight jump would send you into orbit around the asteroid. You could literally escape from Bennu just by pushing hard with your feet. The escape speed is only about 20 centimeters per second, slower than walking speed. The sky would be completely black, dotted with fixed stars that don't twinkle like they do on Earth because there is no atmosphere. The sun would appear as a dazzlingly bright dot, much smaller than we see from Earth because Bennu is, on average, farther from the sun than our planet. The surface under your feet would not be hard, but loose, like deep snow or sand. Each step would raise a cloud of dust that, in the absence of an atmosphere, would move in perfect parabolic trajectories without being slowed down by air resistance. Giant boulders, some the size of a multi-story building, would rise all around, creating a surreal landscape reminiscent of the scenery of a science fiction movie. But staying on Bennu would be extremely dangerous. Cosmic radiation, from which we're protected by the Earth's magnetic field and atmosphere, is not blocked by anything here. Micrometeorites are constantly bombarding the surface. On Earth, they burn up in the atmosphere, but here they reach the surface at full cosmic speed. And periodic particle emissions from the surface can unexpectedly bombard you with rocks and dust. In general, Bennu is not a picnic place, despite all its scientific appeal. However, some scientists dream of a manned mission to Bennu in the future. Imagine astronauts making a months-long journey to this tiny world, spending weeks or months studying it in detail, setting up scientific instruments, perhaps even conducting orbital deflection experiments. It would be an incredibly expensive and difficult mission, but it would give us knowledge and experience that cannot be obtained with robots. What if we didn't think about protecting ourselves from Bennu, but about using it? Asteroids like Bennu contain vast amounts of valuable resources. Carbon, water, metals could all be mined and used in space, avoiding the need to lift materials from Earth's deep gravity well. Water is especially valuable. It can be decomposed into hydrogen and oxygen, creating rocket fuel right in space. This would revolutionize space travel, making long-distance missions to Mars, the asteroid belt, and beyond possible. There are companies that are already planning to extract resources on asteroids. Of course, We're still very far from commercial production on an industrial scale, but the first steps are being taken. Missions like OSIRIS-REx and Japan's Hayabusa 2, which also brought back samples from the asteroid Ryugu, prove that we can reach these objects, study them, and take back material. The next step is to learn how to do it in a cost-effective way. The irony is that Bennu, this potential threat to humanity, could also become one of our most valuable resources in the future. Perhaps in a century or two, we won't be thinking about how to deflect Bennu, but rather how to keep it close by turning it into a space refueling station or a source of building materials for colonies on the Moon and Mars. The future is full of amazing possibilities. But let's get back to the question of collision. How exactly do scientists calculate the probability of impact? It's an incredibly complex task that requires supercomputers and months of calculations. The process begins with observations. Every time Bennu passes close enough to Earth, telescopes around the world record its position with the highest possible accuracy. These observations make it possible to determine the parameters of Bennu's orbit, semi-major axis, eccentricity, inclination, and other characteristics. But the asteroid's orbit does not remain unchanged. The Sun's gravity is, of course, a major factor, but the trajectory is also affected by the gravity of all the planets, especially the larger ones, Jupiter, Saturn, and Earth as well, when Bennu passes by. The solar wind exerts pressure on the asteroid, and as we've already said, the Yarkovsky effect constantly, albeit slowly, changes the orbit. All this must be taken into account. Scientists use the Monte Carlo method, a statistical approach where the calculation is repeated thousands or even millions of times with slightly different initial conditions. Each calculation takes into account errors in observations, uncertainties in the mass of the asteroid, in the strength of the Yarkovsky effect, and many other factors. The computer calculates Bennu's trajectory hundreds of years in advance for each set of conditions. Then it is analyzed in how many cases the asteroid's trajectory intersects with the Earth. The result is not one specific prediction, but a probability distribution. It turns out that in most scenarios, Bennu safely passes by Earth. But in a small percentage of cases, about 0.037%, a collision is possible. Moreover, scientists can tell on which dates the risk is highest. The nearest dangerous date after 2182 is 2290, where the probability of a collision is slightly lower. There's also a risk on other dates in the next centuries. When you adding all these possible collision dates together, we get a total probability of 1 in 2,700 before the year 2300. What is especially important to understand is that these probabilities will be clarified. Every new observation of Bennu, every flyby of Earth, gives us more data. Every year, the uncertainty decreases. It is possible that in the coming decades, scientists will be able to say with almost 100% certainty, no, Bennu will not collide with Earth in 2182, or vice versa. The probability can increase to the point where you have to seriously plan a deflection mission. We just don't know for sure yet. And it's this uncertainty that makes us prepare for the worst. It is worth noting that Bennu is not the only asteroid of concern to scientists. There is an asteroid Apophis with a diameter of about 370 meters, which will fly frighteningly close to Earth on April 13, 2029, so close that it will be visible to the naked eye and pass below the orbit of some communication satellites, at a distance of only 31,000 kilometers from the Earth's surface. Fortunately, recent calculations show that a collision is virtually impossible. But this close flyby will change Apophis' orbit in an unpredictable way, requiring new careful observations. There is also asteroid 2009 FD, which has about a 1 in 100 chance of colliding with Earth in 2185. Asteroid 2000 SG 344 was once considered a serious threat, but additional observations have ruled out the risk of a collision. History is full of such cases. An asteroid is discovered. Preliminary calculations show a possible collision. The world holds its breath. Then new observations refine the orbit, and the threat disappears. This is a normal process, and this is how planetary protection should work: early detection, constant monitoring, clarification of risks. But sometimes surprises happen. In February 2013, an asteroid with a diameter of about 20 meters entered the atmosphere over Chelyabinsk without warning. No one knew about its existence until the moment it entered the atmosphere. It exploded at an altitude of about 30 kilometers, and even at this altitude, the shock wave was powerful enough to shatter windows in thousands of buildings and injure more than 1,500 people. It was a wake-up call, a reminder that our monitoring of space is still far from perfect. On the same day, just a few hours after the Chelyabinsk meteorite, another, much larger asteroid, 2012 DA14, with a diameter of about 30 meters, flew past the Earth at a distance of only 27.7 thousand kilometers. Scientists knew about this asteroid in advance and accurately calculated that it would fly by. The coincidence of two events on the same day was purely coincidental, but it showed how active the outer space around us is. Returning to Bennu. What makes it so special among thousands of potentially dangerous asteroids? Several factors. The first is its size. It's big enough to cause catastrophic consequences, but not so big that we're completely helpless in front of it. A 10-kilometer-long asteroid, like the one that killed the dinosaurs, is so massive that it would be nearly impossible to deflect it with the technology available. But Bennu is in the golden mean where we can theoretically do something. Secondly, its orbit is well studied. Thanks to decades of observations and the OSIRIS-REx mission, we know more about Bennu than the vast majority of other asteroids. This makes it an ideal candidate for the first real planetary defense mission, should it ever be needed. We can plan ahead, develop and test technologies knowing the exact characteristics of our target. Thirdly, the time frame. We have more than a century to prepare, enough time for careful planning, but not so much that the problem can be completely ignored. This creates a healthy sense of urgency that motivates the development of planetary defense technologies now, not when it is too late. But there's also a deeper, almost philosophical aspect to Bennu's story. This asteroid makes us wonder about our place in the universe. For most of human history, we have been helpless in the face of the forces of nature. Earthquakes, hurricanes, floods, droughts, all this hit us, and we could only survive and recover from disasters. Space threats were even more frightening because they came without warning from the abyss of space, against which there was no defense. But now, for the first time in the history of our species, we are not helpless. We can see the threat centuries before it materializes. We can study it, understand its nature, plan against it. We have developed technologies that can change the trajectories of space objects. Humanity has moved from a passive victim of space to an active participant capable of influencing the fate of not only our species, but all life on Earth. This is an incredible achievement, and Bennu is a symbol of this transition. Moreover, Bennu reminds us of the fragility of existence. Our planet is a small oasis of life in an endless, mostly hostile universe. We share outer space with millions of rocks flying at incredible speeds, and from time to time, our paths cross. Most of these encounters are harmless. Small meteorites burn up in the atmosphere, creating beautiful shooting stars. But sometimes, very rarely, an encounter can be catastrophic. The Earth bears the scars of such encounters. The Chicxulub crater in Mexico's Yucatan Peninsula is where an asteroid about 10 kilometers in diameter slammed into Earth 66 million years ago, ending the age of dinosaurs and killing 3/4 of all species on the planet. The Vredefort crater in South Africa, with a diameter of 300 kilometers, is the wake of an asteroid impact 10 to 15 kilometers in size, which occurred 2 billion years ago, when life on Earth was still primitive. The Sudbury crater in Canada, the Papagai crater in Russia, each of them is evidence of colossal cosmic catastrophes of the past. But in between these giant blows, smaller ones also occur. The Tunguska event of 1908 felled trees over an area of more than 2,000 square kilometers, and it was an object only about 50 to 60 meters in size that exploded in midair. If such an explosion had occurred over a large city, millions would have died. The Barringer crater in Arizona, with a diameter of 1.2 kilometers, was created just 50,000 years ago by an asteroid about 50 meters in size. Quite recently in geological terms, when humans already existed, though not in America. Statistically, an asteroid the size of Bennu hits about once every 100,000 to 200,000 years. Sounds rare? Could be. But human civilization has only existed for about 10,000 years since the invention of agriculture. Modern industrial civilization is only about 200 years old. We are still babies by cosmic standards, and we have already seen the Chelyabinsk meteorite. If humanity survives for millions of years, and I hope it will, we will inevitably face such threats again and again. The question is not if this will happen, but when. That is why investing in planetary protection is not an excess, but a necessity for the long-term survival of our species. We are the only known species in the universe that can foresee and prevent its own extinction from a cosmic impact. This is both a huge responsibility and an incredible privilege. Dinosaurs couldn't build spaceships. They could not deflect the asteroid, but we can. And that makes us arguably the most important beings in the known universe, at least in terms of terrestrial life. Bennu's story also shows how far science has come in recent decades. Back in the middle of the 20th century, we didn't even know that asteroids could threaten the Earth. This was considered a problem of the distant past, not related to the present. It wasn't until the 1980s when Luis and Walter Alvarez discovered a layer of iridium around the world dating back to the extinction of the dinosaurs that the scientific community realized that space strikes were a real, ongoing threat. This discovery launched the modern era of asteroid exploration and planetary defense. Since then, we have gone from simply recognizing the problem to actively working on solutions. We have built a network of telescopes to monitor the sky. We have sent space missions to study asteroids up close. We have successfully tested the deflection technology with the DART mission. We brought samples from asteroids to Earth. In just 40 years, humanity has gone from being ignorant of space threats to being actively developing planetary defenses. This is an amazing achievement, and it offers hope for the future. But are we doing enough? This is a question that many experts are asking. Funding for planetary defense programs is still relatively modest compared to other space programs, not to mention military budgets or spending on social programs. NASA's Office of Planetary Defense Coordination operates on a budget of about $150 million a year. That seems like a lot of money, but by comparison, it's less than the budget of one major Hollywood movie. The U.S. military budget exceeds $800 billion a year, 5,000 times more. Even a small redistribution of priorities could radically accelerate the development of planetary defense technologies. Some scientists advocate more ambitious programs. It is proposed to build new, more powerful telescopes specifically designed to search for asteroids, including space observatories that could detect objects approaching from the direction of the Sun, the blind spot for ground-based telescopes. It is proposed to develop and keep in readiness spacecraft for the rapid deflection of asteroids in case of detection of a sudden threat. It is proposed to conduct more missions to different types of asteroids to better understand their diversity. These proposals require billions of dollars more, and policymakers have to make difficult decisions about priorities. But when you think about it from an insurance perspective, it's clear that the cost of preventing a catastrophe is incomparably less than the cost of the disaster itself. An asteroid the size of Bennu's impact could cause trillions of dollars in economic damage, not to mention human casualties. Even a probability of 1 in 2,700 justifies a significant investment in protection. There's another aspect of this story that is worth mentioning: international cooperation. Asteroids do not recognize national borders. If Bennu collides with Earth, countries on the other side of the planet from the impact site could suffer. This is a truly global problem that requires a global solution. Fortunately, the space community understands this. There is the International Asteroid Warning Network and the UN Space Mission Planning Advisory Group, which coordinate the efforts of different countries. This is an example of how a common threat can unite humanity. In a world divided by political, economic, and cultural conflicts, asteroids remind us that we're all in the same boat, a little blue planet flying through space. In the face of an existential threat from space, our differences seem insignificant. Perhaps the work on planetary protection can become a model for cooperation in other areas: climate change, pandemics, biodiversity conservation. Now let's think about the future. What will happen to Bennu and our efforts to monitor it in the coming decades? Bennu's next close encounter with Earth will occur in 2037, when it will pass at a distance of about 7.5 million kilometers, far enough not to pose a threat, but close enough for good observations. Then there will be a close approach in 2060, in 2080, in 2135, and finally a critical approach in 2182. Each of these close encounters will give scientists the opportunity to refine Bennu's orbit. Especially important will be the approach of 2060, when Bennu will pass at a distance of about 740,000 kilometers, about twice as far as the Moon. That's close enough for detailed radar observations, which will allow us to measure the asteroid's size, shape, and even surface details with great precision. This data will significantly improve our understanding of whether Bennu poses a real threat in 2182. By 2060, we will have more than half a century of additional observations after the OSIRIS-REx mission. It is quite possible that by that time scientists will be able to say with 100% certainty, there will be no collision, you can sleep peacefully. Or it may be the other way around. The probability may increase to a level that requires action. In that case, humanity would still have 122 years to prepare for the deflection mission, more than enough time. Imagine what such a mission could look like. Sometime in the 2150s, when our great-grandchildren are adults, an international coalition of space agencies launches a fleet of spacecraft to Bennu. Perhaps it will be a combination of approaches: a gravity tractor for slow, steady deflection, a kinetic impactor for rapid speed changes, and several scientific probes to monitor the results. The mission could take decades. The ships reach Bennu in the 2160s, operate there for 10 to 15 years, slowly changing the asteroid's orbit until it passes by Earth at a safe distance by 2182. It would be the greatest engineering victory in human history. Not a victory over other people in war, not the exploitation of natural resources, but a triumph of human intelligence and cooperation over the blind forces of the cosmos. The whole world would be watching this mission. Children would study it in schools. When Bennu flew safely past Earth in September 2182, perhaps humanity would have declared the day a worldwide holiday, Planetary Protection Day, a reminder of our ability to shape our own destiny. But there's an alternative scenario, more optimistic. Perhaps by 2182, humanity will have advanced so much technologically that asteroid protection will become a routine procedure. Perhaps we will have permanent bases throughout the solar system, powerful spacecraft with advanced propulsion systems capable of reaching any asteroid quickly. Perhaps we will regularly extract resources from asteroids and have vast experience in changing their trajectories. In such a future, Bennu may not be a threat, but an opportunity. It could be carefully sent into orbit around the Moon or to a Lagrange point between the Earth and the Moon, turning it into a space refueling station or a source of building materials. Of course, this is all speculation about the distant future. But isn't it surprising that we can think so far ahead at all? Our ancestors 1,000 years ago could not have foreseen asteroid threats. They couldn't imagine space travel. They lived unaware of the dangers lurking in the sky above their heads. We know, and knowledge is power, the power to act, the power to protect not only oneself, but all future generations. Bennu's story also makes you think about the legacy. What will we leave to our descendants? Future generations will judge us not only by how we lived, but also by how we prepared for future challenges. If we invest in planetary protection now, if we develop technology, if we conduct research, if we train the next generation of scientists and engineers, we are giving our descendants the tools to protect themselves. This is perhaps the most important gift one generation can give to the next. Not wealth, not comfort, but the ability to survive and thrive in the face of unknown future threats. And Bennu is just one asteroid among thousands. Every new discovered near-Earth asteroid needs to be tracked. Every orbit needs to be calculated. Every potential threat needs to be assessed. It is a never-ending task that requires constant vigilance. But it is a task that we can accomplish, a task worthy of our intelligence and our technological power. So what do we do now, knowing about Bennu? Panic? Of course not. The probability of a collision remains low, and even if it happens, it will not happen in our lifetime and not in the lifetime of our children. Ignore? Also no. That would be irresponsible to future generations. The right approach is to continue what we do: observe, research, develop technologies, plan. Take it seriously, but don't go to extremes. For the average person, Bennu's story is a reminder of the fragility and preciousness of life on Earth. Every day we wake up under clear skies. Every moment we spend with loved ones, every achievement of human civilization, all this exists thanks to the successful geography of space. We live in a relatively quiet corner of space, on a planet with a protective atmosphere and a magnetic field, at a safe distance from our star. This is incredible luck, and we should not take it for granted. At the same time, Bennu's story is a source of pride. We are a species that has gone from caves to spaceships, from stone tools to technologies that can change the trajectories of asteroids in just a few millennia. We have deciphered the laws of physics that govern the universe. We have understood our place in space. And now we're using this knowledge to protect our home. If it's not admirable, I don't know what is. The asteroid Bennu flies through space as it has for billions of years, indifferent to the existence of life on Earth. He is neither malicious nor benevolent. He simply is a rock in space, following the laws of orbital mechanics. But its existence and its trajectory have been the catalyst for incredible human achievements. The OSIRIS-REx mission, the development of planetary defense technologies, international cooperation, and the expansion of our knowledge of the origins of the solar system and life. In this sense, Bennu is a gift of perspective, a reminder of our vulnerability and our strength, a gift of time that allows us to prepare for a possible meeting in a century and a half. The gift of knowledge. Samples from its surface reveal the secrets of the ancient past. And the gift of purpose, uniting humanity around the common task of protecting our common home. So when you look up at the star-studded night sky, know this: Bennu is flying somewhere out there, invisible to the naked eye. An ancient messenger from the dawn of the solar system, a potential threat to our distant future, an object of scientific study, and a symbol of our ability to withstand cosmic challenges. His story is not over yet. The climax will come only on September 24th, 2182, when our distant descendants will either celebrate a safe flight or look up at the sky in anxious anticipation. But I believe, based on all that humanity has achieved over the past centuries, on our ingenuity, our courage, our ability to solve seemingly impossible problems, I believe that when the time comes, we will be ready. We will protect our planet. We will ensure that the history of life on Earth, which began 4 billion years ago, continues for billions of years into the future. And perhaps someday, thousands or millions of years from now, our distant descendants will remember Bennu not as a threat, but as a turning point, the moment when humanity first truly realized its place in the universe and took responsibility not only for itself, but for life on Earth itself. It is a legacy worth fighting for. It's a story worth telling. And this is a future worthy of being built, starting right now.